Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Corrado Böhm, a name perhaps less widely recognized than some of his contemporaries, stands as a pivotal figure in the history of computer science, his work forming a cornerstone upon which much of modern programming practice is built. His intellectual journey began in the fertile ground of early compiler design, a field then grappling with a fundamental challenge of translating high-level programming languages into machine-executable code. This pursuit quickly expanded into a deeper investigation of computation itself, leading to the conceptualization of the CUCH machine, a theoretical construct of profound significance. The problem Böhm aimed to solve through the CUCH machine was one of code reusability and portability, a pressing concern in the nascent era of computing. Different hardware architectures demanded different machine codes, effectively locking software to specific platforms. Böhm envisioned a universal machine, one capable of executing programs written in a standardized, hardware-independent language. This language would then be translated into the specific machine code of whatever computer was available. The CUCH machine achieved this through a clever application of universal combinatory logic. Combinatory logic, pioneered by Haskell Curry, provides a way to represent any computable function using a small set of primitive combinators. Böhm recognized that this could serve as an intermediate language, a lingua franca for computation. Programs would be written in this combinatory language and then interpreted by the CUCH machine, which could be implemented on any hardware. Specifically, the CUCH machine used a set of reduction rules to simplify combinatory expressions. These rules, derived from Curry's work, specify how to rearrange and simplify expressions involving the basic combinators, such as a's, k, and I. The machine repeatedly applies these rules until the expression is reduced to a normal form, representing the result of the computation. Consider a simple example. Suppose we want to represent the function that duplicates its argument. In combinatory logic, this can be expressed using the s and k combinators. The expression skk, when applied to an argument x, reduces as follows: skkx becomes kxkx, which further reduces to xx. Thus, skk is equivalent to the duplication function. The CUCH machine would take this expression, skkx, and apply the reduction rules to arrive at xx, effectively executing the duplication. Böhm drew direct inspiration from Alonzo Church's lambda calculus, a formal system for expressing computation based on function abstraction and application. Church's work demonstrated the power of lambda calculus as a universal model of computation, meaning it could express any computable function. Curry's combinatory logic offered an alternative, equivalent system, one that Böhm found particularly amenable to implementation in hardware. The influence of these two giants of mathematical logic is undeniable in Böhm's work. Böhm's insights extended beyond the theoretical realm of universal machines. His collaboration with Giuseppe Jacopini led to a result of immense practical importance of the Böhm-Jacopini theorem. This theorem, though seemingly abstract, had a transformative effect on how software is written. Prior to its publication, programs were often characterized by complex control flow riddled with go-to statements that jumped arbitrarily from one part of the code to another. This style of programming, often referred to as spaghetti code, was notoriously difficult to understand, debug, and maintain. The Böhm-Jacopini theorem provided a rigorous foundation for structured programming, a paradigm that advocates for the use of a limited set of control structures: sequence, selection, and iteration. Sequence refers to the sequential execution of statements. Selection, typically implemented using if-then-else statements, allows the program to choose between different paths of execution based on a condition. Iteration, commonly achieved using while or for loops, enables the repeated execution of a block of code. The essence of the Böhm-Jacopini theorem is that any program, regardless of its complexity, can be rewritten using only these three control structures. This result provided a theoretical justification for the elimination of go-to statements, paving the way for more structured, understandable, and maintainable code. While a detailed examination of the Böhm-Jacopini theorem's proof and implications will follow, it is crucial to recognize its place within Böhm's broader contributions. His work on the CUCH machine demonstrated the possibility of hardware-independent computation, while the Böhm-Jacopini theorem provided a blueprint for writing programs in a structured, disciplined manner. These two achievements, though distinct, are united by common thread, a deep understanding of the fundamental principles of computation and a commitment to making those principles accessible and applicable. Böhm's legacy extends far beyond these specific results. His work laid essential groundwork for functional programming, a style of programming that emphasizes the use of functions as first-class citizens. Functional languages, such as Lisp, Haskell, and ML, owe a significant debt to Böhm's pioneering work on combinatory logic and the CUCH machine. The principles he championed continue to resonate in modern compiler design, where techniques for code optimization and transformation are often rooted in the theoretical foundations he established. In conclusion, Corrado Böhm's contributions to computer science are profound and far-reaching. From his early work in compiler design to his conceptualization of the CUCH machine and his collaboration on the Böhm-Jacopini theorem, Böhm consistently pushed the boundaries of what was possible, leaving an indelible mark on the field. His work not only addressed immediate practical problems, but also laid the conceptual foundations for future innovations, solidifying his place as a true visionary. Böhm's intellectual journey took a pivotal turn with his collaboration with Giuseppe Jacopini, culminating in the groundbreaking Böhm-Jacopini theorem. This theorem directly confronted a central problem in the burgeoning field of computer programming: the quest for a structured approach to program design. Early programming practices often relied heavily on go-to statements, which allowed for arbitrary jumps within the code. While seemingly flexible, this approach frequently resulted in complex, difficult to understand, and error-prone programs, often referred to as spaghetti code. The challenge, therefore, lay in demonstrating that any computable function could be expressed using a limited set of control structures, specifically sequence, selection, if-then-else, and iteration, while loops, thereby eliminating the need for go-to statements altogether. The Böhm-Jacopini theorem provided a definitive answer to this challenge. Formally stated, the theorem asserts that any program, regardless of its complexity or the number of go-to statements it contains, can be transformed into an equivalent program that uses only these three fundamental control structures. This equivalence is crucial. The transformed program must compute the same function and produce the same output as the original program for all possible inputs. The original proof, published in 1966, employed mathematical notation to rigorously demonstrate this transformation. While the specific notation may vary depending on the formal system used, the core idea remains consistent. Let P represent an arbitrary program containing go-to statements. The theorem guarantees the existence of a structured program P' composed solely of sequence, selection, and iteration, such that P and P' are computationally equivalent. This equivalence can be formally expressed using concepts from computability theory, showing that both programs compute the same partial recursive function. The proof itself is constructive, outlining a step-by-step procedure for eliminating go-to statements. The key lies in introducing auxiliary variables and restructuring the control flow using nested, if-then-else statements and while loops. While a full, formal exposition of the proof would delve into intricate details, the essence can be captured through a simplified example. Consider a hypothetical program segment with a go-to statement in 1 / some code 2 if condition go to 4, 3 / more code 4 / target of the go to this program segment can be transformed into an equivalent structured program as follows: Boolean flag equals true, while flag / some code originally at line 1 a condition / code to reach the target originally at line 4 flag equals false / exit the loop when the target is reached, else / more code originally at line 3 flag equals false / exit the loop. After executing this block, this simplified example illustrates the core principle by introducing a Boolean flag and encapsulating the original code within a while loop. The go-to statement can be effectively replaced by conditional execution and loop control. The actual transformations used in Böhm and Jacopini's proof are more complex, handling arbitrary numbers of go-to statements and intricate control flow patterns, but the underlying idea remains the same: to systematically eliminate go-tos by restructuring the program using sequence, selection, and iteration. The impact of the Böhm-Jacopini theorem extended far beyond theoretical computer science. It provided a solid theoretical foundation for the emerging field of structured programming, which advocated for a more disciplined and organized approach to program development. One of the most influential voices in this movement was Edster W. Dijkstra, whose 1968 letter, Go-to Statement Considered Harmful, became a rallying cry for the adoption of structured programming methodologies. Dijkstra's work, while building upon the theoretical groundwork laid by Böhm and Jacopini, focused on the practical implications of go-to statements. He argued that their unrestricted use made programs difficult to read, understand, and maintain, increasing the likelihood of errors. Dijkstra's critique resonated deeply with the programming community, contributing to a widespread shift away from go-to-based programming towards structured programming techniques. It is important to note that Dijkstra's emphasis was on code readability and maintainability, directly influenced by the theoretical guarantee that any program could be written without go-tos. The Böhm-Jacopini theorem, therefore, served as a catalyst for a paradigm shift in software engineering. It demonstrated the theoretical possibility of writing programs without go-to statements, which in turn paved the way for the development of structured programming languages such as Pascal and C. These languages provided built-in support for sequence, selection, and iteration, making it easier for programmers to write well-structured and maintainable code. The principles of structured programming, rooted in the Böhm-Jacopini theorem, continue to exert a profound influence on modern software engineering practices. While modern programming languages offer a wider range of control structures beyond the basic three, the underlying principles of modularity, code clarity, and maintainability remain central to software design. Object-oriented programming, for example, builds upon structured programming by introducing concepts such as encapsulation, inheritance, and polymorphism, but the basic building blocks of control flow still rely on sequence, selection, and iteration. Furthermore, modern software development methodologies, such as agile development and test-driven development, emphasize the importance of writing clean, well-structured code that is easy to test and maintain. These methodologies are direct descendants of the structured programming movement, which in turn was inspired by the theoretical insights of Böhm and Jacopini. The legacy of the Böhm-Jacopini theorem extends even to the realm of formal methods and program verification. Techniques for formally verifying the correctness of software often rely on structured programming principles to simplify the analysis. By ensuring that the code adheres to a well-defined structure, it becomes easier to reason about its behavior and prove that it meets its specifications. In essence, the Böhm-Jacopini theorem provided a crucial link between theoretical computer science and practical software engineering. It demonstrated that any program can be expressed using a limited set of control structures, thereby laying the foundation for a more disciplined and organized approach to program development. Its influence can be seen in the design of modern programming languages, the adoption of structured programming methodologies, and the development of formal methods for program verification. The theorem stands as a testament to the power of theoretical insights to shape the practice of computer programming. The principles of structured programming, solidified by theorems like Böhm and Jacopini's, extend even to the realm of formal methods and program verification. Techniques for formally verifying the correctness of software often rely on structured programming principles to simplify the analysis. By ensuring that the code adheres to a well-defined structure, it becomes easier to reason about its behavior and prove that it meets its specifications. In essence, the Böhm-Jacopini theorem provided a crucial link between theoretical computer science and practical software engineering. It demonstrated that any program can be expressed using a limited set of control structures, thereby laying the foundation for a more disciplined and organized approach to program development. Its influence can be seen in the design of modern programming languages, the adoption of structured programming methodologies, and the development of formal methods for program verification. The theorem stands as a testament to the power of theoretical insights to shape the practice of computer programming. Böhm's profound impact on the foundations of computer science continues with his exploration of lambda calculus and type theory, areas where he tackled fundamental questions about computation and expressiveness. Within lambda calculus, a central challenge lies in understanding the properties of type systems. A type system assigns labels or types to expressions in a programming language, allowing compilers to verify that programs are well-behaved before execution. This prevents many common programming errors, enhancing reliability and security. Polymorphic type systems, a particularly expressive kind, allow functions to operate on arguments of multiple types, increasing code reusability. A fundamental question arose: can one algorithmically determine whether a given lambda term possesses a valid type within a polymorphic type system? This is the type inference problem, and Böhm provided a definitive answer: it is undecidable. Böhm's proof of the undecidability of type inference in the polymorphic lambda calculus is a landmark result. The problem he confronted was this: given a lambda term, can we determine whether it is a type according to the rules of a polymorphic type system? His approach involved a clever reduction from the halting problem, a classic undecidable problem in computer science. The halting problem asks whether a given Turing machine will eventually halt when run on a specific input. It is known that no general algorithm can solve this problem for all possible Turing machines and inputs. Böhm demonstrated that if one could solve the type inference problem for the polymorphic lambda calculus, one could also solve the halting problem. He achieved this by constructing a specific lambda term whose typability is directly linked to the halting behavior of a Turing machine. In other words, the lambda term would have a valid type if and only if the corresponding Turing machine halts. The core of Böhm's proof lies in encoding the behavior of a Turing machine within a lambda term. This encoding involves representing the Turing machine's state, transition function, and input type using lambda expressions. The construction is intricate, requiring careful manipulation of lambda calculus rules. The resulting lambda term is designed so that type checking it effectively simulates the execution of the Turing machine. If the Turing machine halts, the type checker will succeed in assigning a type to the lambda term. If the Turing machine runs forever, the type checker will fail. To illustrate, consider a simplified example, although the full construction is far more complex. Suppose we want to represent the state of a Turing machine as a pair of lambda terms, one representing the left part of the tape, and the other representing the right part. A transition function could then be encoded as a lambda term that takes the current state as input and produces the next state based on the Turing machine's rules. By repeatedly applying this transition function, we can simulate the execution of the Turing machine. Böhm's genius lay in devising a way to express this entire process within a single lambda term whose typability reflects the machine's halting behavior. The implications of Böhm's undecidability result are profound. It means there exists no general algorithm that can automatically determine whether a given program in a polymorphic language is type correct. This limitation has shaped the design of type systems ever since. While full type inference is impossible, practical type systems often employ restrictions or approximations to achieve decidable type checking, while still providing strong guarantees about program correctness. Böhm's work had a direct and substantial impact on the development of practical type systems. His findings directly influenced Robin Milner and Roger Heinle, whose independent work led to the creation of the Heinle-Milner type inference algorithm. This algorithm, while not capable of inferring types for all lambda terms, provides a powerful and decidable type system that forms the basis for type checking in many functional programming languages. The Heinle-Milner algorithm achieves decidability by imposing certain restrictions on the polymorphism allowed in the type system. It uses a technique called unification to infer the most general type for an expression. While it cannot handle all possible polymorphic lambda terms, it strikes a balance between expressiveness and decidability, making it practical for use in real-world programming languages. The legacy of Böhm's work on type theory is evident in the design of modern programming languages. Languages like Haskell and ML, which rely heavily on type inference, owe a significant debt to Böhm's theoretical insights. These languages use type systems to catch errors at compile time, improving program reliability and reducing the risk of runtime exceptions. Type theory also plays a crucial role in program verification, where formal methods are used to prove that software meets its specifications. By providing a rigorous framework for reasoning about program behavior, type theory helps ensure the correctness and security of critical software systems. The influence extends beyond programming language design. Type theory has found applications in areas such as data validation, ensuring that data conforms to predefined schemas, and in the development of secure communication protocols, where types can be used to enforce security policies. The ongoing research in type theory continues to push the boundaries of what is possible in programming language design and verification. Building on the foundation laid by Böhm's groundbreaking work, the quest for more expressive and reliable type systems remains a central theme in computer science, driven by the desire to create software that is both powerful and trustworthy. The exploration of computation extends to the fascinating realm of self-interpreters, programs capable of executing themselves. This concept, seemingly paradoxical at first glance, holds profound implications for understanding the nature of computation and its potential for self-reference. The challenge lies in creating a program that can both parse and execute its own code, effectively acting as its own virtual machine. Corrado Böhm tackled this problem with characteristic ingenuity, devising a self-interpreter for lambda calculus, a foundational formalism in computer science. Böhm's approach involved encoding the syntax of lambda calculus within the lambda calculus itself. This encoding allowed the self-interpreter to treat its own code as data, manipulating it according to the rules of lambda calculus. The self-interpreter essentially simulates the evaluation process of lambda expressions step by step until a final result is obtained. This achievement demonstrated the inherent computational power of lambda calculus, showcasing its ability to represent any computable function, including itself. A key element in Böhm's work is the Böhm transformation, a technique for representing data structures within lambda terms. The Böhm transformation provides a way to encode pairs, lists, and other data types using only lambda abstractions and applications. This encoding relies on the ability of lambda calculus to represent functions and to apply functions to other functions, effectively creating a system where data is represented by its behavior. Consider, for example, the encoding of a pair of values, say A and B. Using the Böhm transformation, this pair can be represented as a lambda term that takes a selector function as input. This selector function determines which element of the pair to return. If the selector function is true, the lambda term returns A. If the selector function is false, it returns B. This encoding demonstrates how data can be represented by its response to different operations, a fundamental concept in functional programming. Specifically, let's represent true as the lambda term lambda x lambda y x, which selects the first argument. Similarly, let's represent false as the lambda term lambda x lambda y y, which selects the second argument. Then the pair A, B can be represented as the lambda term lambda s s of B. When we apply this lambda term to true, we get lambda s s of B lambda x lambda y x, which reduces to lambda x lambda y x of b, which further reduces to a. Similarly, when we apply to false, we get b. This illustrates how the Böhm transformation allows us to encode data structures within the pure lambda calculus. Böhm's work on self-interpreters had a significant influence on later research in denotational semantics, a branch of computer science that focuses on providing mathematical meaning to programming languages. Denotational semantics uses mathematical functions to represent the behavior of programs, allowing for formal reasoning about their correctness. Böhm's self-interpreter provided a concrete example of how a programming language can be given a denotational semantics within itself, paving the way for more sophisticated semantic models. Furthermore, Böhm's ideas found application in the development of functional programming languages. Functional programming emphasizes the use of functions as first-class citizens, meaning that functions can be passed as arguments to other functions, returned as values from functions, and stored in data structures. The ability to manipulate functions in this way is essential for building self-interpreters and for encoding data structures using the Böhm transformation. Languages like Lisp and Scheme, which embrace functional programming principles, owe a debt to Böhm's pioneering work. The concept of a self-interpreter also has practical applications in areas such as metaprogramming and virtual machines. Metaprogramming involves writing programs that manipulate other programs, either by generating code, analyzing code, or transforming code. Self-interpreters provide a foundation for metaprogramming by allowing programs to treat their own code as data, enabling powerful code manipulation techniques. Virtual machines, which are software implementations of computer architectures, also rely on the principles of self-interpretation. A virtual machine executes programs written for a specific architecture by interpreting their instructions, effectively simulating the behavior of the underlying hardware. The design of virtual machines often draws inspiration from the techniques used in self-interpreters, such as encoding instructions as data and simulating the execution process. Modern applications of self-interpretation extend to the design of domain-specific languages and the implementation of embedded systems. Domain-specific languages are programming languages tailored to a particular application domain, such as data analysis, web development, or game programming. Self-interpreters can be used to implement domain-specific languages by providing a simple and efficient way to execute code written in a specialized language. Embedded systems, which are computer systems embedded within other devices, often have limited resources and require efficient code execution. Self-interpreters can be used to implement virtual machines for embedded systems, allowing them to run code written for different architectures or to execute code that has been dynamically generated. This flexibility is essential for adapting embedded systems to changing requirements and for supporting a wide range of applications. The work of Alonso Church on lambda calculus provided a direct influence on Böhm's exploration of self-interpretation. Church's development of lambda calculus as a formal system for expressing computation laid the groundwork for Böhm's work, providing the theoretical foundation upon which Böhm built his self-interpreter. The elegance and expressiveness of lambda calculus, as demonstrated by Church, inspired Böhm to explore its potential for representing and manipulating programs within itself. Daniel Scott, a prominent figure in denotational semantics, was significantly influenced by Böhm's self-interpreter. Scott's work on developing mathematical models for programming languages drew inspiration from Böhm's demonstration that a programming language can be given a semantics within itself. Böhm's self-interpreter provided a concrete example of how programs can be represented as mathematical objects, paving the way for Scott's more abstract and general semantic models. This influence underscores the lasting impact of Böhm's work on the theoretical foundations of computer science. Böhm's contributions, spanning the CUCH machine, the Böhm-Jacopini theorem, type theory, and self-interpreters, coalesce into a powerful legacy that profoundly shaped functional programming, compiler design, and theoretical computer science. A common thread of abstraction and formalization binds these diverse achievements, revealing a consistent pursuit of rigor and elegance in the foundations of computation. The CUCH machine, conceived as a concrete realization of Church's lambda calculus, demonstrated the feasibility of a universal computational model based on function application. Its significance lies in its early exploration of functional programming principles, predating many of the languages that would later popularize these ideas. The machine's design, emphasizing the manipulation of functions as first-class entities, foreshadowed the core concepts of languages like Lisp and Haskell. John McCarthy, the creator of Lisp, was undoubtedly aware of the theoretical underpinnings of the CUCH machine, and its influence can be seen in Lisp's emphasis on functional abstraction and its reliance on lambda expressions as a fundamental building block. The CUCH machine served as a tangible example of the computational power inherent in lambda calculus, inspiring others to explore its practical applications. The Böhm-Jacopini theorem, a cornerstone of structured programming, provided a theoretical justification for the elimination of the go-to statement. This theorem demonstrated that any program, regardless of its complexity, can be expressed using only three control structures: sequence, selection, and iteration. This had a transformative impact on programming methodology, leading to more readable, maintainable, and verifiable code. W. Dijkstra, a staunch advocate of structured programming, directly cited the Böhm-Jacopini theorem as a key justification for his arguments against the indiscriminate use of go-to statements. Dijkstra's influential essay, Go-to Statement Considered Harmful, popularized the principles of structured programming and contributed to its widespread adoption. The theorem's impact extends beyond programming style. It also influenced compiler design, enabling the development of more efficient and reliable code generation techniques. Compiler writers could rely on the theorem to optimize code based on structured control flow, leading to improved performance and reduced errors. Böhm's work in type theory further solidified his commitment to formalization and abstraction. His investigations into the properties of type systems contributed to a deeper understanding of the relationship between programs and their meanings. Type theory provides a rigorous framework for reasoning about program correctness, enabling the detection of errors at compile time rather than at runtime. Robin Milner, a pioneer in type theory and functional programming, acknowledged the influence of Böhm's work on his own research. Miller's development of the ML programming language with its sophisticated type system, drew inspiration from Böhm's emphasis on formal verification and type safety. The principles of type theory, as championed by Böhm and others, have become increasingly important in modern software development, particularly in safety-critical applications where reliability is paramount. Böhm's self-interpreter, a remarkable achievement in theoretical computer science, demonstrated that a programming language can be defined within itself. This concept, known as metacircular interpretation, has profound implications for language design and implementation. A self-interpreter provides a concise and elegant way to specify the semantics of a language, enabling programmers to understand its behavior in a clear and unambiguous way. It also serves as a powerful tool for language experimentation and evolution, allowing developers to modify and extend the language without altering its fundamental structure. Mitchell Wundt, a prominent researcher in programming language semantics, built upon Böhm's work on self-interpretation to develop more sophisticated techniques for language definition and implementation. Wundt's work on denotational semantics and abstract interpretation drew inspiration from Böhm's demonstration that a programming language can be treated as a mathematical object, amenable to formal analysis and manipulation. The enduring relevance of Böhm's ideas is evident in modern programming paradigms and software engineering practices. Functional programming, with its emphasis on immutability, higher-order functions, and declarative style, has gained widespread popularity in recent years. Languages like Haskell, Scalar, and F# embody the principles that Böhm championed throughout his career. Compiler design continues to rely on the theoretical foundations laid by Böhm and his contemporaries. Techniques such as static analysis, code optimization, and formal verification are essential for building reliable and efficient software systems. The formalization of computation, a central theme in Böhm's work, has had a transformative impact on the development of new computer languages. Researchers continue to explore new ways to represent and manipulate programs as mathematical objects, leading to more powerful and expressive programming tools. The impact of Böhm's work on the formalization of computation is undeniable. His contributions provided a theoretical basis for the development of new computer languages, influencing the design of languages as diverse as Lisp, ML, and Haskell. He provided concrete examples of abstract concepts, making them accessible to a wider audience and inspiring others to explore their potential. His insights into type theory, self-interpretation, and structured programming have had a lasting impact on the field, shaping the way we think about and build software systems. Corrado Böhm stands as a pioneer whose work continues to inspire researchers and practitioners in computer science. His relentless pursuit of abstraction, formalization, and elegance has left an indelible mark on the field, shaping the foundations of functional programming, compiler design, and theoretical computer science. His legacy serves as a testament to the power of ideas and the enduring value of fundamental research.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.